In this video, we derive Laplace's law for pressure vessels, which describes the stress in the wall of vessels as a function of the pressure. So pressure vessels are things like balloons, arteries, compressed air cylinders, or even bacterial cells under osmotic pressure that are any sphere or cylinder-shaped object that has pressurized contents inside a thin wall. We're particularly interested in thin-walled pressure vessels where the radius of the sphere or cross-section of that cylinder, which is what we see here with this cut in the XY plane. So in this situation, the radius of the cylinder is much greater than the thickness. And because it's much greater, we don't even worry about whether it's the inner or the outer radius. We just call it one radius. And in these pressure vessels, the inside of this is exposed to a pressure P, which is pushing outward, thus tending to stretch this vessel. So to calculate how stress and strain depend on the pressure, the radius, and the thickness, we'll start with spherical pressure vessels. Because of symmetry, we can take any little element on the surface of the sphere oriented in any direction, and the stress in these two directions should be the same. So we'll just call it sigma, and that refers to the plane stress. And I say plane stress because no matter where we take on the sphere, if we take a small enough element, we don't see the curvature of the sphere and it looks effectively like a plane. So now we'll take this and we can cut here. Here we'll cut a plane here in the XY plane, and we look at this a little bit from the side, and we're going to calculate here what the stresses would be in this object. So if we replace the missing half of this, the piece that we've taken away here, just like we've been replacing these missing parts of the cut with internal loads, we'll point out here that there's internal stresses. So we know that we have tension as this vessel is stretched, and this tension is sigma. And the entire vessel wall will be under this sigma. But we'll also have a pressure because the missing lumen that we have here is pushing on this, just because the pressure pushes in all directions, but we're just asking here, what are the stresses perpendicular to the cut? That is, stresses in the x direction. So we're just interested in those pressures that are going directly in, although pressure is also going in all these other directions. Now, we'll look at this and we want to integrate the stresses over all of these areas in order to get the normal force at the cut. So we've said we have sigma coming in, we have pressure coming out, but the force on the material will be, and this is the force due to that sigma, is going to be the area that the stress acts over times that stress. Now the area we're talking about here is just the area of the material here. So this area is, we could look at it and say it's the inner and the outer radius, but because it's thin-walled, we can also think of it as that it's the whole length of that wall is the circumference 2 pi r, and then we multiply that by the thickness. And so the force then is just 2 pi RT times that sigma. Then the force on the pressurized contents, now this time we're asking about the area here in the lumen of this. And so the area in the lumen of this is the force due to the pressure, is the area times the pressure, because that's the relevant thing. And noted the pressure is going in the negative x direction, so we'll put a negative there. And that's then the area of a circle is pi r squared, and then we multiply that by p. So then we can rearrange this. We know that the sum of this must equal 0. And that means that we have 2 pi r t sigma must be equal to, I forgot the negative up here, but when that goes on the other side to say sigma due to the force is negative sigma due to the pressure, that negative sign goes away. We get pi r squared p, and then we can cancel all the terms that are in both sides. We'll cancel one of the r's, getting rid of the squared up here. And so then we rearrange that to say what we see down here, which is that the stress is equal to P times R divided by 2P. We refer to this as Laplace's law for spherical pressure vessels. So we're also interested in thin-walled cylindrical pressure vessels. Now in this case, the stress is asymmetric because in this direction along the length of the cylinder, we call that sigma L, the longitudinal stress that runs here in the x direction. Whereas we also have this stress, the circumferential stress that's running around the circumference, so is anywhere in the y or z directions or in between them. This is similar to the theta direction that we talked about in the torsional loads. We also call the circumferential stretch the hoop stretch or I should say a lot of people call it that, especially when they look at arteries, which are a type of cylindrical pressure vessels. So in this case, if we cut this in half in the xy plane, like we see here, we'll again see the same thing we saw before, where we have the stress, but this time it's sigma c, we have the pressure, and this looks identical to the free body diagram we drew for cylinders. So because it's the same diagram, we get the same values, and what we learn is that the Laplace's law for cylindrical pressure vessel tells us that the longitudinal stress is also equal to PR over 2T. But if instead we cut this in the XY plane, so what we're going to do here is to make a cut like there, but run it all the way along the length there. And so we'll get what we see here at the lower part. So now our stress in the material is pulling straight out here, and this is the circumferential stress that was going out there, and it's pulling straight at us in the z direction, whereas the pressure is going right into here in the lumen, also in the z direction, but into the board instead of out of it. And so we can do the same thing we did before where we added these up. The force due to the stress is the stress, the circumferential stress, times the area it works on. And the area it works on now is these two surfaces there, because we're going to do this thing over that rectangle that we're seeing in the cut. So those two circles, or those two lines there, two very small rectangles, have an area, the length. That's what we'll call this area here, the length, and I should say this had a radius here. So it's the length, and then what we have here also is the thickness t, and we have two of them, so it's just twice that. Then the contents now are, this distance here is now twice r, and so the force due to the pressure is the pressure. Again, it's acting in the negative direction into the board there, times L times 2 times R. Again, we rearrange these to solve that sigma C is equal to P times L times 2R, and then we'll divide by this part up here is L times T times 2. And we will again cancel the parts that show up in the top and the bottom. And this time what we see is Laplace's law for cylindrical vessels for the circumferential stress is the PR over 2 that was left, and we've carried over here from the previous board for the longitudinal stress. And so these are the values that we've calculated.